So the next part of the question is to calculate the density of the bathtub. And so we're starting out with 120 kilograms as the mass, and then we calculated the volume of the tub. And so you'd simply divide 120 by 202. And this is what I get in my calculator, 0.594059406 kilograms per liter. And obviously we're not going to use all of those numbers. We have to round it using our rules for significant figures. Because I'm dividing here, the rule for when you multiply or divide is to use the least number of significant figures. So here we have two significant figures for 120. This is a leading zero. It's to the left of the decimal place, so there's only two significant figures here. For this number, there's three significant figures. This is a sandwich zero, so there's three there, and so our final answer should only have two significant figures, and so our final answer would be 0.59 kilograms per liter for the density of our bathtub. Now we need to talk about the difference between the word precision and accuracy. So in the lab, when you're doing measurements and those values are similar, if you measure something 3 times, for example, and you get the same number or numbers that are very similar to one another, we refer to that as the number being precise, okay, because your measurement is basically you're able to repeat the measurement and get values that are similar. A measurement is considered accurate when the value is actually close to the true or accepted value. For example, if I wanted to determine the density of water in the laboratory, so I made several measurements of the mass of the sample of water and the volume of the sample of water. When I did my calculation, if I got the density of the water to be 1.00 grams per milliliter, that's pretty good because that is actually the accepted density value for water. So that in that case, that data would be very accurate. If I did multiple experiments, measurements where I got the density of water to be 1.0 grams per liter every time, it would also be precise. So I'd have had that same value over and over again. That would mean my data was also precise. So here's a picture of explaining the differences between accuracy and precision. And this is something that you've probably seen before. Here we have targets, and someone is shooting at a target, and they shot 3 shots, and they were all on the bullseye here. In this case, because we're looking for the bullseye when we're doing experiments, we're looking to be able to determine with very high accuracy the true accepted value sometimes. If that were the case, then our values would be close to the accepted value would be the bullseye, right? So here we have 3 values that are very close to one another too. So they shot 3 arrow shots that are very close to one another, and so it's also precise because there's very little differences each time they shot the arrow. Here's an example where you have precision, where you have 3 shots that are very close to one another, but they're not at the center of the bullseye here. So these arrows shots here are precise but not accurate. Okay, and here we have 3 shots that are kind of far away from one another, so they're not precise, and they're far away from the target area, so they're not accurate either. You have to understand the difference between precision and accuracy in terms of when you're experimenting in the lab, and be able to use that the vocabulary of accuracy and precision. Here's another example. We have a data set here, and so it says here that cough medicine is delivered by a 10-ounce dispenser, and that volume is 296 milliliters. So if you look at the data set here, the value is 283, 284. It's not really close to 296 at all, right? So you would not say that this dispenser one is very accurate. Okay, but if you look at the similarity of the numbers here, they're very close to one another. So you would say that dispenser number 1 is precise because the numbers are very close to one another. They're precise but not accurate. Dispenser 2 here is more accurate than dispenser 1, okay? But the numbers are sort of everywhere. See, 293, 289, I'm sorry, 298, 296. So the numbers are moving around a lot, and so definitely not precise, but more accurate than number 1. So you have some values here that are 296 exactly. So that's an accurate value there, but the precision is not there. And then data set number 3 for dispenser number 3, it has values that are very close to 296 or 296 exactly. So you have precision in this case because the values are very similar, the numbers are very similar to one another, and you also have accuracy because we know that the real true value is 296 milliliters. So in this case, dispenser 3 has both accuracy and precision. Alright, so the last section of chapter 1 is dealing with dimensional analysis, okay, and involves math calculations using dimensional analysis to carry out unit conversions. Okay, so in science, a lot of the times the units are not the units that we are going to be using based off the tools that we have in the lab, and so you have to be very used to converting one unit to another. And so this mathematical approach is referred to as dimensional analysis. We're really using the units to guide you in order to how to set up the mathematical problem. This is something that is not new to you. You've been doing this probably since elementary school, okay, when you've converted pints to quarts and quarts to gallons and all of that stuff. That's all dimensional analysis. Now that's using the English system. Of course, we're going to use the SI system, but the concept is exactly the same. So I'm hoping that you guys already have experience doing this. I know you do, but remembering how to set this up, I'll show you quickly how I use dimensional analysis. Now, it's really important to understand the concept and be able to do these conversions very easily, simply because you're going to be doing this type of thing throughout the whole year of chemistry. So this semester for sure, when we start to do stoichiometry, that's nothing really, if you think about it, it's just nothing but dimensional analysis and conversions. So whenever you're doing dimensional analysis, you have to make sure you write in your units. And so here, the most important part of dimensional analysis, of course, is knowing your conversion factors. So what is a conversion factor? So you guys probably know that 12 inches is equal to 1 foot. And so in the SI system, of course, we don't use feet. We can convert inches to centimeters. So here is an example of a conversion factor for converting inches to centimeters. 1 inch is equal to 2.54 centimeters. So there's two different ways you can express conversion factors. And of course, we express them in terms of fractions. So you can write it as 2.54 centimeters over 1 inch, or 1 inch over 2.54 centimeters. Okay, this is important because when you're doing your conversions, the units are really important to write out, because the units are going to tell you how to do your calculations and set up your problem. Here are some other examples of common conversion factors. Okay, 1 kilogram is equal to 2.2046 pounds. Okay, 1 quart is equal to 0.94635 liters. So all these different conversion factors, and we're going to learn more conversion factors as we go along. We're going to learn how to use the periodic table to make our own conversion factors. Okay, so this is not going away. It's very important that you understand this concept of dimensional analysis. And if you need more practice, I would suggest you go online, Google dimensional analysis, look up some videos online. There's probably online worksheets you can do, practice problems. I know there's practice problems in your textbook. So make sure you take the time to do some practice problems so that you're very familiar with this. So here we have an example of we're converting 34 inches into centimeters. So here you can see how they have 34 inches, and normally I write this over 1, so 34 inches over 1, and that's just making it a fraction. Okay, and then you're looking at your conversion factor here. So remember before how we said you can write your conversion factor as 1 inch over 2.54 centimeters or 2.54 centimeters over 1 inch. And so how do you pick out that conversion factor? So let me show you. Okay, so here I have the same problem here that's written out, and you can see how basically they use the conversion factor where the units for inches are going to cancel out. If you think about units in general and how, for example, you've been doing this before, when you're doing math, like say I have 5/3 and then I have 4/5. Okay, so I can cancel out my 5's there, right? Because 5 over 5 is 1. Right? So we can also do that with units. So here, if I have inches in the numerator and inches in the denominator, those units can cancel out. And the units I have left, centimeters, and that's exactly what I want, right? I wanted to convert 34 inches into centimeters. So I use a conversion factor and set it up to where my units for inches would cancel out so that I'm left with units for centimeters. Okay? So the units cancel out, but the numbers do not. So that means that you're still doing the math. So you're still going to have to multiply 34 times 2.54 to get 86. Okay? And so technically you're multiplying two fractions. And you remember how to multiply two fractions. You have A over B, and then you have C over D. Basically, it's going to be A times C, so the numerators, right? So A times C over B times D, right? We're just multiplying fractions. Pretty simple. So that's what we're doing here. 34 times 2.54 is 86. 1 times 1 is 1. 86 over 1, we don't see that, but anyway, that's 86 centimeters, right? So that's how you set it up. That's how you do the math. Let's do another one quickly. If I want to convert 55 meters to centimeters, so first I have to know my conversion between my units. What is my conversion factor between meters and centimeters? Well, I know that 100 centimeters is equal to 1 meter. So I can write my conversion factor as 100 centimeters over 1 meter or 1 meter over 100 centimeters. And so how do I set that up? So the first thing I'm going to do, I'm going to write my given information over 1, so 55 meters over 1, just making it a fraction, okay? And then I'm going to put my conversion factor here. A lot of times you'll see me just put it in parentheses there. So which conversion factor do I use? Well, I have meters here for my units because that was my given information. So I need meters in the denominator because I have it in the numerator. So I'm going to use a conversion factor that has meters in the denominator, so my units cancel out for meters, and I'm left with a unit for centimeter, which is exactly what I wanted, right? I wanted to convert from meters to centimeters. And so the next thing to do was my units cancel, I go ahead and do the math. 55 times 100 is 5,500. 1 times 1 is 1 if I wanted to write that as a fraction, but I end up with it being 5,500 centimeters. And that's your final answer. Okay. And the final section here of the first chapter, we have to talk about temperature units. And so you are very familiar probably with the Fahrenheit scale. It's what all temperature in the U.S. is reported in Fahrenheit for sure. And sometimes they give us Celsius values as well. We know that water freezes at 32 degrees Fahrenheit or 0 degrees Celsius. Water boils at 212 Fahrenheit or 100 degrees Celsius. So 100 degrees Celsius covers the same temperature interval as 180 degrees Fahrenheit.